Okay, we're going to get started here. We're going to do 3D concurrent force systems today. So last time we did 2D concurrent force systems. We're going to do the same idea of the concurrent force system where all the lines of actions for each force that's in the system, they intersect at one common point somewhere. So there's one point out there in space somewhere where all of those lines of lines of action intersect. Except now we're going to have them in three-dimensional space. So not just XY plane, but XY and Z plane. Let's look at our web page here. So let's see if there is one thing in here. So this is in Moodle. At some point we're going to use this grid paper right here, this isometric dot grid paper. We're going to use that to help us draw in 3 dimensions because it's not quite as simple as drawing in 2 dimensions. So this paper will help us with that. So if you want to download that, or I don't know if you'll have time to print it out before we get to that or not, but at some point you might want to use some of these little dots. You don't need it right now, but I'm going to use it later on. There's a PDF here of an example problem or two that we'll go through something similar today, but if you want another one, then you can look at that. What we're actually going to do, though, is we're going to start in 2D. So we're going to do that so that we kind of review what we did last time, plus it'll help us set up how we're going to solve our simultaneous equations. Because that's what we're going to end up doing in 3D is we're going to have 3 sets of equations. Remember, we had summation of forces in the x direction equals 0 and in the y directions equals 0. That was for the equilibrium in a 2D concurrent force system. Now that we have 3 dimensions, we'll also need summation of forces in the z direction to equal 0. So those 3 equilibrium equations, and we'll add a 4th later on. Those 3 will ensure that as long as they're true, so all the forces all the force components, anything in the x direction it adds to 0, anything in the y direction separately adds to 0, and anything in the z direction adds to 0. If those are all true, then our object, our free body, is in static equilibrium, which they are in static equilibrium for what we're doing. But like I said, we're going to start with 2D. So this is actually one of the WebWork optional problems. So this is problem 2 on optional set 1. Remember, those are just bonus point problems. So you don't have to do these, but this one would be an easy one to do because we're going to work through it. So I've got it over here in OneNote, and we'll look at it and use this as a starting point for how we're going to get into our 3D simultaneous equation solving. So what we've got here is a collar. So the lightweight collar they're talking about is this little piece. This problem statement does not specify that it's frictionless, but it needs to be frictionless for our purposes. We don't have any information about the friction between the collar and the rod that it's sliding on, so we're going to assume that it's frictionless. You know, these WebWork problems, each person gets their own set of numbers. So if you're looking at yours, your numbers are probably going to be different than what mine are, but they'll be similar, same ranges of stuff, and it'll work the same way. So this collar should be able to slide, you know, kind of towards point C and down towards B, except that there's this cable that has it attached at D, so it can only go certain directions, and then there's a force F, which is basically its weight. So this is a little thing that I colored yellow. My problem says it weighs 600 pounds. So it's not a very little collar. But so it's got this gravitational force trying to pull it down. The cable is sort of holding it, not up, but it's holding it to the right. And the rod is having to hold it upwards. So let's draw this free body diagram out. This is not a free body diagram that we're looking at here. This is just a diagram. I think what I'll do is I'll draw right on top of this and then hopefully select all that and move it away. Hopefully that'll work. So obviously we have force F. Oh, I guess if we're following our order of free body diagram drawing, we identify the body. I'm going to use the collar. We draw the body, so I'm going to, kind of draw over the body here. So there's the body. Then we identify all the forces. So it has its own weight, F. It has the cable force, and it has some reaction from the rod. The rod is doing something to it. So those three forces are going to work on this thing. So cables, chains, ropes, they all work in a similar way where I suppose in an extreme scenario where you've got a giant rope or something, it can support a little bit of a compressive load. But in general, in everything we're going to do, cables, chains, ropes, they can only support tensile loads. So the force in the cable is right in the same direction that the cable is going. So that's fine. We don't know how much it is. It's just the, let's call it tension in the cable. Let's call this one just F, since that's what they called it. We have a coordinate system already drawn on here. Let's use that. So there's the x-axis. There's the y-axis. And we've got some dimensions for angles. So alpha for me is 23 degrees. This will get less cluttery in a minute. Beta, well, beta we can't really do anything with that. We're not going to draw the rod. We're going to draw what the rod is doing to the collar. So since we said it's frictionless, we don't have to worry about friction. The only force when you have a sliding mechanism, so it's a collar on a rod or a pin that's in a slot sliding back and forth, something like that. Whenever there's sliding, rolling, frictionless stuff like that, even if there is friction, this force is the same, but there could be an additional frictional force. But we're only talking about frictionless stuff right at the moment. The reaction for all of those, like this collar on a rod, pin in a hole or a slot, wheels on the ground, something like that, the reaction is perpendicular to the constraint. So the constraint here is rod BC, and so the reaction that rod is applying to collar A is perpendicular to rod BC. So it's going to do something like this, and we'll just call it let's just call it the normal force. We'll call it N, and it's perpendicular to let's do this. Rod BC is perpendicular to that. Now, if there was friction, the friction would be parallel to that little blue dotted line that I drew, but again, we're frictionless. The 33 degrees, it is going to go right here. Now, if that's hard for you to see, then you will have to do things like that, figuring out, what's that angle of that normal force. To me, it's obvious, but if you think through it, how it would work is the rod is 33 degrees from horizontal, right? So that's what beta is telling us. The rod is 33 degrees from horizontal. So a perpendicular force to that angle is 33 degrees from vertical. So that's how I process it. I'm sure there's some other geometry type way to go through that, but if the rod is 33 degrees from horizontal, perpendicular to that rod is 33 degrees from vertical. So I think we've got all of our stuff on here. Now we need to copy it. This is the part I'm not 100% sure will work, but we'll see. Oh, except that I somehow I keep there we go. All right, let's put it over. Well, we can put it over here. Make sure it's on the screen. Yeah. All right. So there's our little system. And what we need to do is, we know one other thing. We know F is 600 pounds. So we actually know that. The problem is actually asking us to solve for the force from the rod, that's what I called N, and the force from the cable, which I called TC, tension in the cable. Now that I'm thinking about it, I kind of want to move this down below so that everything's kind of in a straight line over here. More like that. Okay. So this is a 2D system. We're not doing 3D yet. We're doing this one so that we can set up the process for doing our simultaneous equations and kind of to review the 2D system. This problem did not say Yeah, it didn't explicitly say that we're in static equilibrium anywhere. We are assuming that for this course, whenever we have some problem like this, if it doesn't say that we're in static equilibrium, we are in static equilibrium because the whole course is built on that. So assuming that we are in static equilibrium, then we have our two, in this case because we're in 2D, equilibrium equations. Summation of forces in the x direction equals 0. Let's expand that equation to put all the x components in here. So I've got the tension in the cable has an x component that would be cosine of 23 degrees. So TC times the cosine of 23 degrees would be the x component of that force, TC. I drew it going, or well, I gave it a positive sign because it's going in the positive x direction. N, the normal force, is going in the negative x direction, so I'll give it a minus N times not the cosine of 33 because 33 is measured from the y-axis. So the sine of 33 degrees. If those parts are confusing you, the cosine and sine parts, then you need to go back and review some sine, cosine, and tangent definitions because we will end up doing them a lot, particularly in the first third of the course. They drop, well, the second third also has some. The last third doesn't, it has the fewest amount of that, but the first third of the course, the first exam one, is heavily built on being able to do sines and cosines and tangents and things like that. So make sure you're up to speed on that. The equation says that if I take all the x components, add them together, they have to equal 0. I did not put f in there because it doesn't have an x component. It's going straight down. There's nothing that specifically says that, except that I know it's the gravitational force, and I don't have anything that tells me that it's not going straight down, so I'm going to assume it is, which it is. All right, so that's our equation. I can't solve that. It has two unknowns, TC and N, so I can't do anything with it. So let's write the other equation. Summation of forces in the y direction equals 0. I'm going to put these in the same order. So I'm going to do TC, N, and then if there's any constants. I'm doing that on purpose to set up how we're going to do our simultaneous equations. So TC is pointing downwards a little bit. So that's my negative y direction. So minus TC times the sine 23 degrees. N is clearly pointing up, so it's going to get a plus N times the cosine 33 degrees. And those, well, I could do this two ways. I'm going to actually put equals 600 pounds. But you could do it this way if this makes a little more sense. So minus, because it's pointing down, minus 600 pounds equals 0. But for the purpose of how I want to solve this set of equations, it will be better to have all of the numbers that don't have variables associated with them. So the 600 pounds doesn't have a variable. The others do. They either have TC or N. It would be better for those numbers, those constants, sometimes they're called residuals, to be on the right side of the equal sign. So that's why I'm really going to write this like this. And when I move it to the other side of the equal sign, it is not negative anymore, it's positive, because I moved it to the other side of the equal sign. Yes, somebody put the SOHCAHTOA thing in the chat for the sine, cosine, and tangent definitions. That is true. I didn't learn it that way, but I have heard that, and it's correct. Now, what we have is we have a system of linear, so they're linear equations. Linear equations means that a couple of things. It means, well, three things. It means that I don't have any variables multiplied by other variables. So I don't have anywhere where TC is multiplied times N. So it means that. It means that there are no transcendental functions of variables. So I don't have sine of N. So I don't have e to the n power or something like that. and it means that all of the powers associated with the variables tc and n are power 1. So in the chat there's a question about, and again, the chat is delayed by like 30 seconds, so it might not answer right away. But what you'll use primarily for looking when you're considering which expression to use, some of it takes experience, just getting familiar with, I need the x component, so how am I going to get the x component? And there are a couple of ways to approach it. I have done it long enough that it is, I don't even know how I do it. It just appears. But one way, if you're having trouble, is take your positive x-axis, measure everything counterclockwise from the positive x-axis. So instead of that 23 degrees, I'd have 360 minus 23. That would be the measurement. Instead of the 33 degrees, I'd have 90 plus 33 degrees. So everything measured counterclockwise. Well, I guess when I'm doing this, it might look clockwise to you. So everything counterclockwise from the positive x-axis, and then all of your x components will always be cosine, and they'll all be plus, so all be positive, and you'll let the cosine itself take care of the negative signs. And all of your y components will always be positive sine. So if you're having trouble with it, you can always resort back to that. It does make it a little bit more cumbersome just because you have to go and convert every angle measurement to being measured from the positive x-axis counterclockwise. But if you're having trouble, then that will always work for you. Just make them all positive and measure all your x components will be cosines, all your y components will be sines. And it will, maybe we'll work one at some point, not today because we already started this one, but I'll work one, I guess, Wednesday that way, just so you can see how that works if you're having trouble with it. All right, back to our linear set of equations. So ours are linear. We don't have TC times n. We don't have cosine of n anywhere. All the variables TC and n are their only two variables. They're all raised to the power 1, even though it's not shown. None of them are TC squared or n cubed or anything like that. So I have linear equations. I have two of them, and the two variables I have are in those equations. So that means I have a set of linear equations. And I can use linear algebra to solve them. Now, your calculators, your whatever calculator you have, there's a good chance that it will do sets of equations. You just have to know how to put them in there and solve it. I'm using something that's a little more generic here so that it will work on any calculator that can do matrices. All right. So what I need to do is I need to create three matrices, A, B, and X. So the A matrix, I'll write that up here. A matrix is the coefficient matrix. So the coefficient, actually let's start with X, the variable matrix, because it's easier. The X matrix is the one that contains all your variables. So our variables are TC and N. So that'll be our variable matrix. Let's do B next because that's even simpler. This is the one that's sometimes called the residuals, and sometimes it's called the constants. I'll use constants. So for us, let's see if I can do multiple colors here. Let's do this blue. So the B matrix would be the constants that are any of the numbers that aren't associated with variables. So they're not variables and they're not coefficients of variables. So that would be the 0 and the 600. And that would mean that our coefficient matrix, those are the coefficients. They could be 0, but they're the coefficients that go with the variables. So those are the like color-coded set of matrices. So how I arrange this is I do, let's do it over here. I do A matrix times X matrix equals the B matrix. So what that looks like when I put the actual equations into this is going to be A is my coefficients. So cosine 23 degrees, which is a number. Like I could calculate that number. I'll leave it. We'll let MathCAD calculate the numbers. So cosine of 23 degrees. The next one is minus sine of 33 degrees. So this top row is my x equation. Ooh, let's do summation of forces in x. The second row is summation of forces in y. It doesn't matter that x is the first row, y is the second row. That's just the way I wrote them out when I did it. What does matter is that all the same variables are lined up in columns. So this column is going to have the coefficients for all of the TCs, and this column will have all of the coefficients for the n's. So the y equation coefficient for TC is minus sine of 23 degrees. The n column coefficient for, in the y equation, the coefficient for n is cosine 33 degrees. So that little matrix is the A matrix. I need to multiply it times the X matrix. Or, well, X being the variable matrix. So this is, see how I wrote TC and N up above those columns? This is those variables in that order. So TC is first, N is second, but it's a vertical matrix, not horizontal. So if I were to multiply those out, like if you may or may not know a lot of linear algebra stuff at this point, but if you took those two matrices and multiplied them together, you would get the two equations we just wrote up above. You wouldn't get the 0 and 600 yet, but you'd get those two left-hand side of the equal sign. You'd get those two parts of the equation. And then equals the B matrix, which is 0 and 600. Those have units of pounds on them. And now that matrix, or those three matrices, those are the matrix version of the two equations, the equilibrium equations that we just wrote. Let's get some room here. Oh, that's not making room. Let's move that down. There we go. This is A times X equals B. That's what this is telling me. Now, again, you may not know linear algebra yet. That's fine. But as long as the A matrix has an inverse, so it should for anything that we're going to do. If you're unsure, then a matrix has an inverse as long as its determinant is not 0. So you have to calculate its determinant. It had to be anything other than 0. Then it does have a matrix inverse, and we can do this process because we need the inverse. So how we would solve this would be we take the inverse of A. So that's not like A to the -1 power. That's in linear algebra. That's how you would say the inverse of A. Multiply times A. A is already multiplied times X. We have to multiply both sides by the inverse. I realize I'm putting little dots there. That's probably confusing. I'm just going to write it like that because it's not dot. This A inverse times A, that is the identity matrix. So again, if you don't know what the identity matrix is, that's fine. It just means that it returns itself. So that's fine. So that just means that this left-hand side just becomes X. It's sort of like it becomes 1. So X times 1 is just X. It's sort of like that. And the right-hand side becomes A inverse B. And X is our variable matrix. So if I can take A inverse times B, so the inverse of A multiply times b, I will get out the values for the variables, which is what I want. You can do that by hand, but we're actually going to do it in MathCAD. So we're over here in MathCAD. We need to make those three those three matrices, which means I have to remember where the matrix option is. Don't remember. Oh, there's a tab called matrix. All right, insert matrix. We want a 2 by 2. That'll be A. So A equals, let me get rid of this thing. A equals a 2 by 2 matrix. And we're going to put in our coefficients for A, which were cosine. Now remember, MathCAD is particular, and it thinks all of these are radians, so I need to put degrees. This one would be negative sine 33 degrees. This one would be negative sine of 23 degrees. And this one would be positive cosine of 33 degrees. So there's our A matrix. Our B matrix is the constants or the residuals. So B is a 2 by 1 matrix. The first one was 0 pounds. Second one was 600 pounds. If you don't put the units on here, that's fine. But don't put units on one and not the other. And X, the values for the variables, will equal A. In MathCAD, you actually do use the same process of creating an exponent to create the minus 1. So A minus 1, and then we're going to multiply that times B. And it will equal, let's put it in pounds, these two numbers. So the 584 is in the top slot. So if we go back to our setup here, the top slot was TC. So the 584 should go with TC. So I'm just going to therefore, MathCAD says, or we'll do MathCAD. Therefore, TC is equal to, and it was 584.4, and N equals 987.7. Those were pounds. Oh, we're just barely on the screen. There we go. So 584 and 987. Those would be the values for the tension in the cable and the normal force in that the rod is applying to the collar that it was the collar that weighed 600 pounds. Now the good thing about this linear algebra, well, this is called what's it called? Matrix inversion method. So since we're inverting the A matrix and multiplying times the B matrix to solve the problem, this can extend to matrices of any size, which means that I can have any number of simultaneous equations, as long as they're linear equations. I do need those three rules: no variables multiplied by each other, all the variables have power 1, and there's no transcendental functions where I have like cosine of one of the variables, cosine of x or y or z or something. Then I can put as many simultaneous equations as I have into that process, A, X, B, then, and solve for the values of those variables. So for 3D, we only need one more. We only are going to have 3 equations, X, Y, and Z. And so this will work for that. Now, if you're solving, a 10 by 10 or something like that, it does get pretty difficult. Certainly by hand, it would be impossible. MathCAD, I don't remember its let's see. Looks like it can do 12 by 12s is what MathCAD can handle for the matrices side. And that's a pretty big system of equations. So it does have limits just on the calculations to do that many matrices or that large of a matrix. It's only 3 matrices, but the A matrix can get pretty big. So, but for 3 by 3, it'll be fine. All right. I don't see any questions, so I'm assuming that means we're generally okay. So now it's time to figure out some 3D stuff. So let me... Oh, let's see. We'll cover... I think we'll just do this. Well, no, I can't squeeze it because it needs to stay. We'll just write on it and then we'll move it out of the way. All right. So this is our isometric grid, dot grid. So there are some that have lines and a whole bunch of other things on them. They all have this pattern though. So isometric means equal measure. So it means that I have, it's set up to where if I draw a three-dimensional object in this or on this grid, that it doesn't have perspective. So you know, like how you, let's go over to the side. Can I go over the side? Well, we'll just go over here to the side. You know how if you look at a cube in perspective, you get something, I'm exaggerating it, but something like that, where it tapers off into the distance. So that has perspective built into it. The isometric does not have that. So if I drew the same cube, but on isometric paper, it would look 1, 2, 3, 4. So I'm drawing it a 4 by 4 cube. So there's, and you know, I didn't do a super great job of drawing my lines perfectly straight, but you can see how it's different from the one I freehanded. It has no perspective built into it. And each of the sides is the real scale. If I were to take a ruler, I guess you can't see me take a ruler, but if I took a ruler and measured those sides, they would all be the same length the way I drew them, because I drew it all four dots in each direction, basically. So that's useful when we're trying to calculate things in 3D, because I'm trying to draw force vectors in all these weird directions, and it's nice if they are equally measured versus they have some perspective involved with that. So to create a coordinate system here, I will pick some point. I'll do this one as my origin. And the x-axis, there's a couple of different ways you can create the x, y, and z axes. I'm going to use the process where z is up. So z is up. Sometimes z is the one that's coming out towards you, but I don't know. It's just easier for me to remember when z is up. So that would be my z-axis. Whoops. Let's try and get it a little straighter. This one, it does matter which one you put here, x or y. This is the x, and this one is the y. It matters because we have a thing called the right-hand rule. So, right hand, whoa, wow, that got all messed up. Rule. So, for the right-hand rule, you take your right hand. Now, this might be mirrored. I don't know when you're looking at it because it looks like that's my left hand. You take your right hand and you take your like your pointer finger and your middle finger and your thumb, and you have to align your pointer finger with the x-axis and your middle finger with the y-axis, and whichever way your thumb points. So it's either going to be pointing up or down, right? So this is x, this is y, and z is either up or down. That sounds like contrived or whatever, but the reason that we need that is that we need to be able to assign directions to, we'll call them moments for now. You may not know what those are yet, but that's fine. We'll get to it later. So we do need a particular pattern for x and y. So it probably looked inverted from looking at it on the screen. because of the mirror image of the camera. But it's your right hand. And another way you can think of it, if you don't like the figuring out where your X and Y axis, you curl your fingers from the X to the Y axis. So for me, if I'm looking at my paper, I would have to curl this direction, and your thumb will point in the direction of the positive Z. So you might have to do that a couple of times in person, not looking at the screen that's probably mirrored. But without doing that, then we won't all be consistent on some things later on. So we have to have the right hand rule. So that means that X has to be this way, Y that way, and Z up. When you go to, got a right hand thumbs up. So in the event that you have to create one of these coordinate systems yourself, then follow that right hand rule. It won't matter right now for the things that we're doing. It'll be later on. Actually, not that much later on. It might be Wednesday when we actually need it. Now, that's just our coordinate system. Now we need to put some forces in this coordinate system. So I'm going to draw one out here. So if I just draw the arrow like I did here, then it's still pretty confusing, because you might look at that and think, oh, that's in the YZ plane. Or you might think that's in the XYZ or the XY plane pointing backwards. Or maybe it's in the XZ plane kind of pointing backwards and up. So it's an arrow by itself doesn't really help. You need the endpoints, or you need a point on that line. So one point, we're still in concurrent force system, so one point is going to be the origin, right? But we need another point on this graph, on this arrow somewhere. So I am going to do it this way, where I'm going to, well, let's see, let's use green. I'm going to drop down to the XY plane, and then go over to the y-axis, and then back to the origin. So in my y direction, I actually went 2 dots, so whatever the dots are worth, inches or meters or millimeters or whatever. In the x direction, I went 1, 2, 3, 4, 5. I went 6, but I went in the negative x direction, so that's negative 6. And then 1, 2, 3, 4, 5. I went up 5. So this endpoint right here would have the coordinates x would be negative 6, y would be 2, and z would be 5. I know it's getting kind of cluttered there with the dots everywhere, but we need the dots. So you're either going to have that coordinate x, y, z set, or you're going to have these lines with the measurements on them directly, like the 2, the negative 6, and the 5. You'll have one of those, or both. You might have both on some problems. But those are going to be how we tell where this force is actually going. All right. I don't see any new questions over there. Let's go and let's build us a problem to solve. So I've got this little guy. Let's get that out of the way. Got this little drone here. We're going to put him kind of in the middle. So he's going to be in a coordinate system. And it's going to be the same type that we just had, where there's y, there's x, and there's z. Okay. We'll probably do the same thing here, where we draw it and then we remove it, remove the background, because the dots do get really a lot to look at. Some of these actually have all the dots connected with lines, and that gets a whole lot to look at. But on paper, that might not be so bad, because you can kind of have them grayed out, dim. But on the screen, it's a lot. All right. So this drone has 3 things acting on it. It has its own weight pulling it down. It has some wind trying to push it in one direction, and then it has its props trying to move it off in another direction, but not straight up. And we've got those three force vectors. So the weight, we're just going to make the weight go straight down. And we're going to make it, let's see, 1, 2, 3, 4, 5. Let's make these to scale. So it's going to be 10. Each dot is going to be 2 for us. Can I do? I can do full scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we can do full scale. So, well, technically, this has 0 for the X component, 0 for the Y component, and -10 for the Z component. Okay. The wind is pushing this thing. Let's do some dotted lines. So -10 this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the way out to there. So that's -10. 7 this way. 1, 2, 3, 4, 5. Oh, that just barely fits. And then 8 up. 1, 2, 3, 4, 5, 6, 7, 8. I think I did them right. So there's the end point. There's the beginning point. Let me see if I can get a ruler to draw that long of a line. All right, so something like that. Now, that one, if I drew that without the X, Y, and Z on there, it kind of looks like it's just in the negative Y direction. But it's really coming towards and to our left a little bit. So its actual X, Y, and Z coordinates are X of 7, Y of -10, and Z of 8. Oh, scroll up a little. Oh, yeah. Let me fix that. There's nothing down there but a -10, but there it is. And then we'll move the dots in a minute to make it a little clearer. All right, so this is the wind load. This one's gravity. And then we need the thrust. So the thrust, I've got it going in the Y direction 5. So 1, 2, 3. No, that's 2, 3, 4, 5. In the X direction, I've got it going -6. 1, 2, 3, 4, 5, 6. And then I've got 12 up, so we may not can fit this one. I have to scroll it back down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It goes right up there. So I'll move it back in a second. So that one is, let's see, X of, this is 6, -6, and this is 12. So X of -6, Y of 5, and Z of 12. All right. See if we can get it to all fit at one time. There we go. So now let's see if I can get rid of our dots. There we go. So on an exam, you'll get some picture like one of these. It'll have just the vectors with the X, Y, and Z labels on them, or it might have the little lines with the numbers on them, like the 5, the -6, and 12 might have those, and you have to come up with the X, Y, and Z coordinates of the endpoint, or something like that. You'll have something like that. One of these two styles is generally what we'll have on the exams. And there's some in web work, so you can look at what different styles are in web work in the homework. All right. Now, this is where we take a little bit of a departure from how we did the 2D stuff. It's the same principle, but there are no signs. Everything is a cosine. So maybe it would be good to remember what sine and cosine and tangent mean, particularly cosine. So let's put us off to the side. This is not part of the problem. This is just an explanation. So we're back in 2D over here. So There's a force vector. Oh, it's under my head. There we go. There's a force vector, and it has an angle that it makes. We'll call it theta, with the x-axis, and that angle, if we did the cosine of theta, it would equal the x component over the hypotenuse, which is just the magnitude of the vector. And if I want to know the x component, which is usually what I want to do, is equal to the hypotenuse, which is the magnitude of the vector, times the cosine of theta. Now, if we take and disassociate this thing from x and y and just say that it's an axis, the same thing is true. So whatever axis I'm looking at, x, y, z, or if I have some other axis that I'm looking at, the angle between that axis and the hypotenuse, or the magnitude of the vector, if I take that angle, call it theta, and use the cosine of theta for that angle, that hypotenuse, then I will get the length of that hypotenuse or magnitude along that axis. Maybe that will make a little more sense once we start doing it. So what I'm going to do is I'm going to write out the same equations, summation of forces in x, summation of forces in y, and summation of forces in z. Let's see if I can get them to where they are all... it's not going to be... I might have to shrink it down some to fit everything on here, but we can do x, I think. So I've written summation of forces in the x direction equals 0. So let's... Oh, I didn't write one thing. This vector that the last one that we drew, that one was thrust. So that's the drone's propellers moving it in some direction, but not straight up. It's moving it kind of away from us and up. All right, so this summation of force in the next direction says that what I need to do is I need to write the, let's do it this way, the thrust component in the x direction plus the wind component x direction plus the x direction of the gravity. Those have to add to 0. So that's the generic way of writing that. This doesn't actually help us because there's no actual information there other than just kind of what the equation means. So let's write the thrust, the x component of the thrust. So if I wanted to find the x component of the thrust, the x-axis is kind of coming out towards me. It has a x component. It's at the very top of the screen, but -6 is the x endpoint of the thrust. It started at 0, 0, 0 at the origin. Remember, this is a concurrent force system, so all the forces will intersect at some point somewhere. I made that point kind of right here in the middle of the drone, and that's where all the forces intersect. So the x component of this guy will be same idea over here. I take the hypotenuse, which is the thrust vector itself. Now, I do have, do I want to do that right now? I think I do. I do have the length of this thrust vector. I haven't calculated it, but I have all the stuff to find it. So let's write, let's put it, I'm trying to not make it too cluttery. I'm going to write right here. I want to say that the length of the thrust vector, so let's do LT, equals the square root of -6 squared plus 5 squared plus 12 squared. So that equals, I've got my calculator over here to do that because I don't know. Let's see, 6 squared plus 5 squared plus 12 squared. is 205. Square root of that is 14.317. So I'll just call it 14.3. Call it that. Let's do that for all of them. So this one, the length for gravity, that's just 10. That one we don't even have to do anything. It's 0 squared plus 0 squared plus 10 squared. Take the square root is 10. So let's do the length over here for the wind. Is the square root of x is 7. Y is negative 10. But we square it. And z is 8. So 7 squared plus 10 squared plus 8 squared, 213. The square root of that is 14 point, we'll call it 6. I'm not too worried about the units here, if these are what these units are. These could be, you know, in another situation, these could be cables that are holding something, and these are actual dimensions. For us, they're forces, so like the thrust force and the wind force and the gravity force, and the dimensions are representing different magnitudes in all those different directions, but they could be distances too in other settings. So now I've got these lengths, and I have, let's go back to our equation. So we'll come back to those lengths. We need them in a minute. I was just kind of preloading that we need them here in a second. Now, what we wrote is summation of forces in x equals 0. We wrote we need to add the x component of thrust to the x component of wind to the x component of gravity, and they all have to add to 0. So how do we get x components? Well, x components equal the hypotenuse. So I'm over here at my little, oh, that's ugly. They equal the hypotenuse times some cosine of angle, theta. That theta is the angle between the wind, the thrust, and the gravity. So whichever one I'm looking at, that vector and whatever axis I'm looking at. So in this case, the x-axis. So the thrust will, the x component of the thrust will be, let's just call it T for thrust, times cosine of theta between the thrust and the x-axis. We'll come back and fill that in a second. Plus the wind, I'll call that W. So wind, W wind is the actual force from the wind, so the total force. So the wind is equal to, or the x component of the wind is equal to the magnitude of the wind times the cosine of the theta that is between the wind and the x-axis, plus gravity, we'll call that G. We could have called that weight because it's how much the drone weighs, but G times the cosine of theta, where that theta is the angle between the G vector and the x-axis. And those all have to add to 0. Okay? That's getting closer to useful, but it's still not quite useful enough. I need all these cosine theta tx, cosine theta wx, cosine theta gx, all of those need to be, I know what they are. I need an actual number for them. I have all the information in this picture. I have all the information to calculate those cosines. So cosine, let's look at this equation, the definition of a cosine, which is almost under my face. There we go. Cosine of theta, any theta, I wrote x component, but the generic definition is what? Adjacent over the hypotenuse, and the hypotenuse in this case is the magnitude, which the magnitude I have, I wrote it as a length because we were kind of calculating it as a length from the origin out to that end point of the wind or the thrust or the gravity. So the magnitude I calculated as a length, but it could be a force of the force from the wind, the force from the thrust, and the force from the gravity. So all those L's could be F's. That'd be fine. So that and the adjacent side. Now the adjacent side is going to be the x component of the wind, the thrust, or the gravity. So what I can do, and again, this might take you a couple of times of working through problems like these, and you've got several in web work and in the optional web work to practice on. But here's what it's going to look like. T times, instead of cosine theta tx, I'm going to use the definition of cosine theta adjacent over hypotenuse. Take the x component for t, which is, well, it scrolled off the screen, but it's -6, over the hypotenuse, which is, I've labeled it as the length. And that -6 over 14.3, that's a number. It's just a constant number. And it turns out that's the coefficient that goes with t for this equation. So that is the cosine. If I were to take my calculator and figure out the angle theta tx and take its cosine, I would get this number, -6 over 14.3. Plus w times the cosine of theta wx. So that would be the x component of the wind, which I had as 7, over the length of the wind, or the total force of the wind, or the magnitude, maybe that's a better word, magnitude of the wind, 14.6, plus the gravity or the weight of the drone, times the x component of that one's 0. So even though that one's 0, I can't just throw it out. I do need to include a 0 in my matrices. Equals the residual part, which will just be 0. Okay, I think that's fine. I'm trying to see if we've got a problem, but I think that's fine. All right. I think because I wrote gravity as its own vector, that it's going to give us a little bit of a weird situation, but that's okay. All right. Let's write the same thing, but let's write our y equation. So I'm going to short circuit that one, and we'll have t, because we need all of this first column. Remember we're trying to build a matrices. So we need all the first column to be the same variable. It doesn't matter that it's t, they just all have to be the same. So I put t first, so they all have to start with t. X, y, and z equations all have to start with t. So t would be cosine of theta ty. So the y component for our thrust was 5. The length, or the magnitude of t, was 14.3, so that's the same. Plus w, the wind, is -10. It has a -10 for its y component, 14.6 for its magnitude, plus g, there's a 0 there, equals 0. And then z is, again, we have to have t in the first spot. The thrust has a 12 for a z component. W has an 8. And G has a -10 over 10. So that's the G is the part that I'm a little bit concerned about, but I think it'll work. We'll find out, because I don't know. It could be possible I end up with a set of equations that have multiple solutions, and that might give us a problem, but we'll deal with that when we get to there. We'll figure it out. All right. Or it could just be that, well, I know that they all have one solution. One solution is that all the forces are 0, right? So MathCAD may tell me that. We'll see. Let's build our matrices and see what happens. So our A matrix is all of the coefficients. So we could go in and calculate these as numbers. 6 divided by 14.3 and so forth, but I'm going to write them this way. Well, that's a 0. We can do that. And you'll start to see patterns on how this works. So there's our A matrix. Our X, remember, this is all the T column. This one is W down that column, and this was G down this column. Those have to be the same order, T, W, and G, in our X matrix. And then our constant matrix, I have them all zeros, so I think MathCAD is not going to like that. And it'll give us one solution where T, W, and G are just all 0, which that is technically true, but it's not what we want. But we'll deal with that when we get there. All right, so now to solve this, we do X equals A inverse times B. We're not going to invert the A matrix ourselves. We're going to put this in MathCAD and see what MathCAD says to do with this. Let's erase these so it doesn't get confused. A is a, oh, let me get you over in MathCAD. A is a 3 by 3 matrix. And the values of it are, let's see, negative 6 over 14.3. Oh, I'm not typing. There we go. Negative 6 over 14.3. 7 over 14.6. 0. You do have to include the zeros if you have them. They're going to be a problem for us, I think, but that's still fine. 5, negative 10 over 14.6, another 0. 12 over 14.3, 8 over 14.6, and then negative 1. That's all of our A matrix. B is a 3 by 1, and it is all 0, and that's, we may have to do something to add to make this work. We'll do that in a minute. A to the negative 1 times B. Yeah, so that's what I figured it would tell us this way, because that's the obvious solution, right? One way that these all add to 0 is if they just all equal 0 and there's no forces at all. So I think what I want to do is, let's see, let's add what do I want to do? I need a third force. I don't know which one I can easily add. I kind of want to, instead of gravity being the third force, I kind of want to just make it over here. That turns it back into a 2D problem. Is that what I want to do? That would be unstable. Let's see. Oh, I don't have drag. I don't have drag on it. My light just went off. So we could add a drag force. Let's do that. I don't know what it is, but let's go back over here. And let's add just in the negative x direction. Oh, wait, no. Thrust is going that way. Let's add drag this way. Positive x direction. That'll be drag. And somehow we have a dragometer that tells us what this value is. And let's just say that it is -3. I don't know what units we're dealing in here, if these are newtons or pounds or whatever they are. But whatever, they're all the same units. So let's just say that we have a known drag force. It would make a lot more sense to have the gravity be the known force. But since we've already kind of set it up this way, let's just make drag a, not -3, just 3. So that's in my x direction, so that would change my x equation to say that it would change all of these, right? Those all become -3 here. Well, not that one. That's the y equation. And that gives us a -3 in here. So now, and we get actual numbers out. So that's it would have made more sense to make the drag force unknown and give a known gravitational force, but we did it this way for some reason. So what that says is that, and so one thing you have to remember here is that I've drawn a drone. I've shown a drone that you might think of as flying around, moving around everywhere, but again, remember, a drone can stay stationary. And so the drone has the wind, thrust, drag, and gravity forces acting on it. All of these, in our case, are set up to where it's in static equilibrium, because we said we solved these 3 equations. This, and this. We said that all 3 of those equations have to add to 0, or else the thing is not in static equilibrium. And when we actually set it up this way, we get these values. Again, there's my -3 drag force that's in here. So this first one goes with the variable we put in the first column, which is, we put T, the thrust. So it has 17.16 units of thrust. The second row is what we put in the second column, wind. There's a 8.8 unit wind force acting on the drone in that direction that we drew earlier, off and to the left, sort of, up and to the left. So the wind's actually helping to lift it up. And then it has a weight, essentially, what we called gravity, of 19.2 units. All of those will create a situation where this drone is hovering in space. It's not really moving anywhere. Once it starts moving, then that means that these 3 equations on the left, the 3 with the green line through them, are not true, because it is moving somewhere and the forces don't add to 0 everywhere. So this method, though, the linear algebra method, where you build the AB matrix, multiply the inverse of A times B, and you get out your values for your variables, this will work with any set of simultaneous equations that are linear. So as long as they're linear. So you can't multiply any of the variables by other variables. You can't, all the variables have to have exponents of 1, and none of the variables can be inside signs or things like, you can't have sine of x, something like that. If those are true, then you can use this process, and your calculators, all of your calculators, have a way to put, unless it's not a, if it's just a adding, subtracting basic calculator, any of your scientific calculators have a way to put a set of matrices in there and do this calculation. On the homework, the web work, feel free, if you want to, I would not do all of it this way, but feel free to use MathCAD to do the web work problems. But on the exam 1, you'll have at least one problem where you have to do simultaneous, probably 2. There'll probably be one where you do simultaneous 2D and one where you do simultaneous 3D. You'll only have your calculator. So you need to make sure your calculator, you know how to operate it to solve systems of linear equations. You can use this process with the matrices, or you can, if it has an equation solver in it, you can use that. That's fine. But you do need some practice on getting the X, Y, and Z equations, equilibrium equations, into the correct matrices, A, B, and X. And you need practice just solving these problems in general. So start working on the web work. Homework 2 should be open. Homework 1 on web work is due Thursday, I believe. So it's getting close to time. If you have questions about them, send me an email or a Discord chat or whatever to so we can work through some of those questions on the web work. And we'll be back Wednesday. It looks like the stream held up today, so that's good. Hopefully the changes I made actually will keep it that way. And we'll be back Wednesday with are actually beginning the mechanics of materials part. So we'll get into, all right, we put all these forces on an object. What happens to the object? It doesn't move anywhere, but it's going to stretch or bend or twist or do those kind of things. That's what we're going to start on Wednesday. I will see y'all then.